Hello everyone, my name is Cristiano Rodrigues and I'm a PhD student and will present the paper Busted Microarchitectural Side Channel Attacks on the MCU Bus Interconnect, which was co-authored with Daniel Oliveira and Sandro Pinto from University of Minho, Portugal. Well, I'm pretty sure that all of you have heard about Spectrum and Meltdown. The discovery of Spectrum and Meltdown had turned the system secure upside down because these attacks basically demonstrated the dangers of microarchitectural side channels attacks. Since then, we have seen the disclosure of a bunch of powerful attacks capable of breaking and bypassing secure isolation boundaries on a number of processors technologies from the mainly CPU vendors, Intel, ARM, and AMD. But one interesting observation is that among the full computing spectrum, these attacks have affected and targeted so-called microprocessor or application processing units. Basically, these powerful high-performance CPUs are the ones that mainly power the cloud infrastructure, desktops, laptops, mobiles, and routers and gateways. And the reason is very simple. There was a goal over the years to push for the performance of these CPUs, and through cellular architecture and microarchitectural optimization without clear understanding the potential and side effects in terms of security. And each of these clusters embedded on the CPUs with complex microarchitecture, which includes multiple levels of cache and to minimize the gap between the CPU frequency and the memory frequencies. But also they include prefetch, predictors, pipelines with a lot of optimization, out of order execution, speculative execution, and this creates a lot of ground for side channels. But these compute units are just one part of the full computing spectrum. On the other side of the spectrum, you have these teeny tiny uh, computing units that are powered by microcontrollers, which are resource constrained in computing and power and memory, but are still very relevant since they are shipped in the billions annually and are at the heart of so many small embedded and IoT devices. MCUs are resource constrained in computing in power and memory and pretty much are in heavy embedded IoT devices, being harmed the major player with trust zone with Cortex-M family. They have typically a single CPU, few bus masters such as DMI, one or very few memory banks, but have a quite large array of peripherals like UART, SPI, timers, and, and other ones. But these devices are highly deterministic and have a very simple microarchitecture. For example, typically don't have caches and have a very small pipeline, like 2 or 3 stages, and lack support for the virtual memory. So there is a common belief that MCUs are not vulnerable to microarchitectural side channel attacks because their microarchitecture is very simple. Want to challenge the status quo and understand which unique microarchitectural elements on MCUs may create new channels and how can we use that to mount new attacks. Well, it's turned out that we identified the MCU bus interconnect, in particular the timing difference exposed via the arbitration logic as a novel source of side channel. And let's explain how this side channel happen to. The CPU issues a transaction to access a specific data in memory, and since the DMI didn't issue any transaction at the same time, there was no collision in the bus interconnect. Similar, the DMI also tries to access memory, but as there is no collision, it happens to access normally. However, the problem happens when both master CPU and DMA issue a transaction at the same time, and they will create contention on the bus, and just one can go through, being the other one delayed. This creates a timing difference, and to validate the pervasiveness of this channel, we mount a simple covert channel that tries to establish 8 bits channel, and here represent just 4 boards, but on the paper we show on 11. But this pretty covers all the Cortex-M family of ARM, and you can see here that there is a clear, noiseless, deterministic channel in all boards. So, but now we'll explain how we went from a simple observation of a microarchitectural channel to a full-fledged leakage. MCUs have a load and store architecture. This means that only load and stores can access data memory. This is important because it allows us to distinguish between normal instruction that only access code memory and load and stores that access both memories. And by seeing this difference, we can infer when a load and a store is executed by looking at the contention on the bus connecting to the CPU to the memory bank of the data memory. And let's assume that the victim has the most basic script dependent code, the if statement that branch on a binary circuit. So when the secret is 1, the if is executed, otherwise the else is executed. Most of the instructions of the if statement take 1 clock cycle to execute and are constant across execution paths. The main difference is when the branch equal instruction takes the branch that uses 3 clock cycles, otherwise we'll use 1 clock cycle. And when else path is executed, the branch equal instruction will take just 1 clock cycle. So the store instruction will create contention, and we'll see that contention happen on clock cycle t plus 3. The same thing happens on the else, but now with a slightly different, because now the branch was taken and will take 3 clock cycles, and that will make the store create contention on the clock t plus 5 instead of clock t plus 3. Take a note that this code is constant time, but by paths took 7 clocks to execute, so there is no traditional time leakage. However, due to the branch equal instruction, the store relative position change, and a spy monitoring, for example, clock cycle t plus 3 can infer what path was executed when it sees contention there. So if there is contention, you know that the secret if path was executed, and then the secret is 1. So now I will show you how we went from a toy example to a full-fledged attack, which we call Busted. Busted is a single-run microarchitectural side-channel attack that leverages an MCU plus arbitration logic to indirectly steal secrets. So there is 2 types of microarchitectural channels: transient state and persistent state. Transient state are the ones that does not hold any state over time, like execution ports or post interconnect. So when there is the side channel leakage, it just happened at that time and cannot be seen on the future. In contrast, there is a persistent state that typically have a cache-like structure, and that side channel leakage is maintained across time. And typically, side channels have 3 phases. The spy does some attack setup, then the victim executes, and then the spy operates over some side channel data to infer the secret. These 3 phases were not straightforward to implement in our attack, and I will show why. So in application processors, typically they use almost every time the cache as some vehicle to mount the side channel, and the cache is a persistent state channel. And so when the spy mounts the attack, it can see the interference that the victim does on the microarchitectural state of the cache, and from this infer a secret. However, in microcontrollers, we have some slight difference here, because microcontrollers typically don't have cache, so you cannot use this primitive, and typically they are single core, so we cannot have concurrent execution between the spy and the victim. Furthermore, there is only the transient state here, so this will raise more challenge, because now the spy executes, the victim executes and creates contention. However, when the spy executes again and tries to infer some secrets, it cannot see any difference on the state of the bus interconnect because it just not hold the side channel information. So this raises some challenge. First, the spy cannot access past microarchitectural states because the bus is stateless. It cannot also run concurrently with the victim because they are single core. The target of our paper. We also assume that there is some mitigation against previous side channel attacks like Nemesis, and we cannot interrupt the victim, and that the secret must be stolen in a single run because our target processes secret that are ephemeral. And to solve this challenge, we introduce the concept of hardware gadgets, and hardware gadgets leverage the vast array of peripherals that are able to run independently from the CPU. And basically what we do is group together a bunch of peripherals and use them to monitor the bus contention and get the memory trace. So now the spy executes, then the victim executes and creates contention. At the same time that the victim is creating contention, the hardware gadget is taking a trace of that contention. And the spy still cannot see any difference on the bus interconnect, but now he has a trace from the hardware gadgets. And with this new concept, we effectively solve our challenges. And we use this concept of hardware gadgets to mount a proof of concept attack against a smart lock application. And so the smart lock device is powered by a single core microcontroller with trust zone. So we have these two worlds, a secure world and non-secure world. In the secure world, we run a trusted firmware for Cortex-M, and on top of that, we run our victim that interfaces with the trusted keypad, and in non-secure world, we run a spy that wants to steal the pin that the user introduced, and they both share, the spy and the victim, a memory bank, and the spy has these hardware gadgets that are looking at the bus interconnect. So this is a snippet of the code that we target. So this has 5 main structures. There's this read keypad, a read key, then there is a loop that is done in all keys of the keypad, and if the key is not pressed, the else is executed, otherwise the if is executed, and the if is what leaks the secret. So let's see how this can be leveraged to leak. So first, the code reads the state of the keypad, and then it iterates over the keypad in each key, and when there is no key press, the else path is executed. However, when the user pressed the key, the if path is executed, and then this will leak the secret and tell that the secret, in this case, is 2. Busted attack has 2 phases: a profiling phase that is done in a lab setting where we control everything, and an exploitation phase that is done in the wild, so we don't control anything, we just deploy our attack on the non-secure world. On the profile phase, what the attacker does is using some hardware gadgets to profile both if and else path. So the attacker just runs the code and profiles the if path and gets a trace for that, and then does the same for the else path. Then this trace can be used on the exploitation phase to program and configure the hardware gadgets, and you can see here that there is different contention points between both paths. And for example, let's pick contention point 14. So the attacker knows, looking to these traces, that if they cease contention on clock cycle 14, it means that the if path was executed. Otherwise, if there's no contention, it means that the else path was executed. With this, we program several hardware gadgets that we put together and make a smart gadget network. And so there is one gadget that trigger all operation, which will do a loop of 60 times. That is the number of keys that the our keyboard has. There is one detection gadget that will check contention on clock cycle 14. There is a counter gadget to keep track of the loop index, that this will be directly connected to the secret. And there is a auto-sync gadget to keep the synchronism of at the clock cycle with the victim. And then, last but not least, there is the read secret gadget to read a secret when the contention is detected. So how this all happened? So the code, the smart gadget network, and all the hardware gadgets, it's looking at the code execution, and when it sees contention on clock cycle 14, it means that the if file was executed. It means that the user pressed the key, and now we know that the secret is 2 because there was that gadget, the counter gadget was keeping track of the loop index. So the smart gadget network just know that the secret was 2 because it was when on that loop the contention was found. So with this, with this paper, just unveil a new channel, microarchitectural channel that leverages the timing driven exposed via the arbitration logic, and introduce the concept of hardware gadgets to address the challenge posed by mounting a side channel in a microcontroller, and it's a very resource constrained device. And we introduce also the concept of smart gadget network that puts together several other gadgets to exploit a victim and do that in the single run without CPU intervention, and doing that in the background while the CPU is executing. And we successfully present a new attack, proof of concept attack on a smart card network that was able to bypass all state-of-the-art Cortex-M trust zone isolation, and we are able to steal a secret key from the non-secure world in the application that were running on the on top of a trust execution environment on the secure world. So we have four main contributions. So we provide evidence that MCUs are vulnerable to microarchitectural side channel attacks. We provide also evidence and proof of a new class of software-based microarchitectural side channel attacks that leverage the bus interconnection. And we introduced a new concept of hardware gadgets enabling microarchitectural side channel attacks on MCUs. And last but not least, we provide a reference attack that bypasses all trust execution environment protection on the mother microcontroller with trust zone M. So in this talk, we just present Busted, the first microarchitectural side channel attack affecting trust zone M microcontrollers. So if you want to know more, you can talk with me at my Twitter, or if you want to play with the attack, we just release artifacts on this repository, and feel free to go there. Thank you all for attending this online presentation, and hope to hear from you.